Welcome back. We have an important question at the top of the screen that I want you to mull over. A few of you have had kinetics already, and we may need your thought process. Channel your thought process over here for us, please, while we figure out reaction speeds. I think I misspelled therefore here. Oh, capital E. Make it more important. All right, for these propagation steps in chapter 8, why can we say the more exothermic step is faster, and therefore the less exothermic step is the rate determining step? So let's just take a quick look back at our previous reaction. And prop 1 was endothermic. So if you extend that statement to saying, well, of the two, which one's more exothermic, it's pretty obvious. One of them's not exothermic at all. This is therefore more exothermic and faster. So prop 2 would not deserve our attention. If you want to make this reaction work the best, you would do everything you could to enhance propagation step 1. And because the rate determining step is it tells you how fast things can go. You are limited to this step. And we're not answering that question yet. Why is this one the rate determining step? Is the translation to our new question. And here we're coming. Okay. Well, we have to look at what's called reaction spontaneity. And for us, more spontaneous reactions will be a little faster. And that is covered by something called Gibbs free energy, which is news to some of you. We will not be testing you on Gibbs free energy. I will just tell you what it is defined as. And it says you can predict how spontaneous a reaction is. That's what Gibbs free energy does, predicts spontaneity. Delta G less than 0 is spontaneous. And as you might guess, delta G greater than 0 is not spontaneous. It prefers going in the backwards direction. And delta H is the change in enthalpy. We've been calculating those. And that is a major driving force for many reactions, enthalpy. Delta S is a different driving force called entropy. Now, it drives reactions that create randomness. And you don't need to know anything more than randomness is enhanced by reactions that create gas molecules. That's one way. So if you have a reaction like, oh, combustion is the best entropy example ever. Next time you're gazing at a campfire, just wonder at the massive changes in entropy as we convert those wood fuel molecules into CO2 and water gas molecules. That is the driving force in that reaction. And as you increase the heat, it gets even more spontaneous. Entropy is very heat sensitive. Enthalpy is independent of heat. That just is the stability of the reactants versus the products. And exothermic reactions have the potential energy of the reactants in an exothermic reaction is a lot higher than that of the products, and that difference gives us the heat. And for endothermic reactions, the I'm having trouble with the word again. The potential energy of the reactants in an endothermic reaction is lower than that of the products. You might want to review energy diagrams, potential energy diagrams. We'll talk about them on Monday. So, in reactions where entropy is a factor, this is a huge part. In reactions, most reactions don't have entropy as a factor. Then enthalpy is the driving force. In chapter 8, you just have to trust me on this one. Chapter 8 reactions. The entropy change is roughly 0. Our reactants and products, let's just look at our only propagation step 1 and 2 that we've seen before. These are all done in solution, although you can do them in the gas phase, but just they're all done in solution, so there's no gas molecules involved. Even though methane's a gas, here it's in solution, it's dissolved, so it's not a gas. And it's a non-radical reacting with a radical to create a non-radical and a radical. Prop 2 is the same. It's a non-radical reacting with a radical to create a non-radical and a radical. The randomness is almost not changing at all in either reaction. So delta S is 0, which simplifies our life according to Gibbs greatly. If the delta S is 0 up here, then this expression disappears, and delta G is roughly, in chapter 8, reactions, let's move that colon a little bit. Therefore, delta G is the same as delta H, roughly speaking. So that right there says the answer to the question. If delta G less than 0 means spontaneous, then the more negative, the more spontaneous. The more negative, comma, the more spontaneous. And for us, we can just say faster. More negative is faster, less negative is, more importantly, less negative is slower, rate determining step. So remember that, because we're going to use it very soon, like almost right now. You're going to freak out a little bit when you see this one. Why? You've got like 8 boxes. One of them needs to be circled. This is part A is 1 point. It's the point for the whole course that will take the most work. To circle the right set of products. It's only worth 1 point. You circle the wrong product in this question, it's not like you're going to get everything wrong. You're going to lose 1 point. As long as you do everything else right, you're going to get all the other points. So don't freak out on this. But there's a multi-part answer for part A about which box to circle. One product does not need an explanation. I just put it there to see who's paying attention. As of day 1 of this course, you should be able to say, forget about those boxes, Dr. Whitaker. They have carbon with 5 bonds. Bromine, methyl, 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 and vinyl. So 5 bonds to carbon that's not happening. But after that, it's a 3-part question about which boxes to circle, to circle for A. 3-part answer. Remember what we just said about delta H, more negative is faster? Choose. And remember prop 1? Prop 1 forms, I'm just going to remind you, prop 1 forms H bonded to the halogen. So that's a new bond. It's negative, right? So which H bonded to halogen is going to happen faster? I will bring over our table if I can find it. I may have gotten rid of it. I may not have. I just don't know where it is. Here it is. Ah, I got it. Which H bonded to halogen happens faster? The choice in our question is HF or HBr. Remember, you're making them. HF negative 569 is much faster than HBr negative 368. Cross off every box with HBr in it. It's slower. I'm going to write that down. Choose the HX forming. This is the first thing you do. It's going to get rid of half the answers that are remaining. That is faster. In this example, that's HF. All the HBRs gone. Good. B. Let's see with our first example, we only have to go to B. Later, we'll do an example where there's a third part to this discussion. Choose. Let's do it in a different color. Sorry, indecision here. It's the word of the day. B. Choose the product that comes from the easier CH breaking. Now remember, you're breaking it. I want the one that has the lowest positive number. Breaking's always positive. You can't get around that. The CH that has the lowest positive number. So if you look at the three products that are left, the three choices are here, I'll get a number for that. Here, I'll get a different number for that. And here, I'll get a third number for that. And please remember, it's about categories. So before I go look, this is vinyl. The H is on the alkene. This is allele. The H is on a carbon one away from the alkene. This is primary. The H is on a C that has one bond to C, and it's not got a double bond, that's C. Oh, when we go back to allele, allelic, it's also secondary because it has two bonds to C. So vinyl, secondary, allelic, and primary. We've seen the numbers already. Should we just go back to our previous page? These are CHs. 2 pages previous, sorry. Let's see, we wanted primary, which is 418. Vinyl was H on CCC 444. And secondary allelic 357. Can I remember three numbers anymore? I don't even know anymore. Plus 357 right here. Plus 418 right here. I'm not picking a 418 over a 357. It's a lot slower. I'm not picking 444 before any of those. I remembered them. We have a winner chicken dinner right here. That's funny. My chicken dinner is half an hour away. No, 45 minutes. Plus 357. That's the one we got to break. So we're ready to circle our product. It is the product box right here. Circle it right here. It's the one that will form faster. And all that for our first point. Now we're going to do a mechanism for the initiation and 2 propagation steps, and I want the mechanism to make the major product only. These exact words will not change in any way, shape, or form from your test. I stole the wording from Fall 19 T3, but you'll see the same wording on the last 6 years almost of T3. I may have added parts H and I in the last couple years, and they will be on yours too. And those are easy answers. So you're going to like that I added them. And we won't get to those till Monday. So who remembers what happens during the initiation step? Something about the heat, something about the halogen breaking. Well, there's our halogen, BRF, BRF. And so our initiation step we'll do here, B init is a good short form. B, you got to show me the bond between the halogens, and you got to show me the radicals. But where you really get your point is the hooks. No hooks, no points. Trying to make sure you know those are radicals. This computer does not like me drawing dots. It breaks in half. Please show it. I need to start in the middle of the bond and end at one of the halogens. You can do the other one on the top as well. You can do the other one on the bottom instead. I don't care, as long as both hooks start in the middle of the bond and end at a halogen. And remember, that's called homolysis or homolysis, however you want to say it. Now you've got to pick the one that's more reactive. You already circled the one that's more reactive. It was HF. I don't want to hear about BR dot for the rest of this whole exam. If you do BR dot after this, doing anything, it's meaningless. It's not as reactive as F dot, not even close. So your prop one, here's your short form for prop one. You can even do this on the test, P1. I know what you're saying. Prop one, the halogen radical that you just made has to pick off the hydrogen that will give you that product you circled. So draw the organic molecule. It's got a tert butyl down here, goes to a C double C. You got to show me that bond to H there, because you're going to break it in half. Half of it goes towards the fluorine with a hook. Make sure these are hooks. Arrows, you put arrows, you don't get points at all. Hooks. The other half goes onto the carbon that's allylic. That doesn't look much like a hook, does it? You're not sure? Just make sure it looks like a hook and it ends at the carbon. There you go. And my B's in the way here, isn't it? Is that all one thing? Yeah, close enough. Just need a little more room there. And the two species you generate are HF, which is one of your products. HF. You're going to use the energy of that for calculating delta H prop 1. And you made your carbon radical, which you must use in the next step. So it's got a tert butyl, goes up to a C double C, comes up here, has a dot. All right. We need that product to be the reactant in the next prop step is P2. And it's going to hook up with, now if you hook it up with BR dot, you're in trouble. It doesn't do that. You will have killed propagation steps by reacting a radical with a radical. On Monday, we'll talk about it. Explain why termination steps are to be avoided. And the termination steps are here. And you don't know yet, but that's when a radical reacts with a radical, and it's not a good thing. The name suggests it's not a good thing. Would you like to be terminated ever? No. Remember, it's always radical with non-radical during propagation. So what's the other non-radical we haven't used? And you say, we used BRF in the initiation step. I want to remind you, you used one molecule out of a mole. That's 0. You have all of your BRF left. It's still there. It needs to react. This is how carbon gets the bromine. It hooks up with it. The radical provides half the bond. The bromine provides the other half. And there's where your F dot comes from for prop 1. You must generate fluorine radical in prop 2 because it is used in prop 1. Show me you know that. And you've generated your other product here. Oh, it doesn't generate F dot. Yes, it does. Sorry, the other product has a bromine. There you go. There's your prop 1 and your prop 2. So we're moving along nicely here. Provide a mechanism for the initiation and 2 propagation steps. And I'm just going to try to separate prop 2 a little lower so I can put the energies right underneath these things. So reminders, prop 1 and prop 2. Radical reacts with, these are both radicals, reacts with the non-radical and non-radical. These 2 molecules are non-radicals. To create a radical, here's a radical, there's a radical, and another non-radical. Remember, radical plus non-radical gives radical plus non-radical, both reactions. If that's not on your page, you're going to be losing points, and you're probably going to lose more points because you won't be able to give me the right energies if you don't have the right species. So I need to figure out delta H, prop 1 and prop 2, and after that, I'm just going to add up my numbers and get delta H for the reaction. So didn't we do some research already for the H's? Yeah, plus 357 for the secondary allylic H, which is being broken here. Do everything in black here. I don't think we looked up anything else. Are you making any new? Yes, we did. We looked up HF and HBr, and I don't remember the number. Was it, I don't know, 565, negative 565 for HF? Let's find out. HF, 569. Negative 569. Why negative and not positive? Because you're making it. New bond. Delta HP1. This is, I'm going to go out on a limb and say this is not our rate determining step. 569 is a bigger number, and I'm subtracting bigger from smaller, and I'm not using a calculator. So I flip them, and I flip my sign. I got a 2, I got a 1, I got a 2. That's about as exothermic as you'll ever see a propagation step. Please, units. You'll lose a half point if you don't put the units down. Kilojoule per mole. Okay. I am 100% certain prop 2 will not be that exothermic, and therefore prop 2 will be the rate determining step. But let's verify that. We're breaking BRF. It's not going to be a lot of energy, is it? BRF coming right up. BRF, BRF, BR. That's the same thing. You're going to have to put in 234 kilojoules to bust that open. Plus 234. You're making a secondary allylic bond. Why is it allylic? The carbon here is 1 away from an alkene, is allylic. Why is it secondary? The carbon here has 2 bonds to carbon. Secondary allylic CBr, making it is going to be exothermic. How much exothermic? Secondary allylic. The 3 allylics are primary, secondary, and tertiary. Negative 228. Negative 228. Remember that. Ooh, this is actually endothermic, isn't it? Two, 3, 4 minus 228 is 6. Units, please. Delta H for the overall reaction. Don't memorize anything about products minus reactants. This is not Hess's law, although it is. Some of you know what I just said. Some of you have no clue what I just said. Forget you ever heard the name Hess, except if you have to read Steppenwolf or something like that. We've already accounted for Hess's law by that one big statement that says breaking bonds is endothermic and making bonds is exothermic. And then you know everything you need to know about signs. All you have to do is positive for breaking, negative for making, add up the numbers. Positive for breaking, negative for making, add up the numbers. Now, at the end, add up the numbers. Negative 206. Okay, and there we have that. And I think that's a nice spot to stop for now. We're going to talk about transition states after the break. We can do D first, which is the rate determining propagation step. We know enough to do that now, and you're going to have to tell me you know at least what delta G is, and that you have to state your assumption that delta S is close to 0, or else I'm not going to accept your argument at all. So in D, you pretty much have to write this no matter what you're doing for D. This is C. This is C. This is the answer for C. This is the answer for C. D, you've got to tell me when delta S is roughly 0, delta G, you want to write an arrow? I'm a scientist. I'm more into symbols than sentences. Don't tell my English teaching friends. Delta G is roughly equal to delta H. If you don't have that there, I'm taking points off, because delta S is often a very important factor. Here you're saying I can ignore it because it's equal to 0 in these reactions. So the less exothermic, which of those two numbers over there, 6 or positive 6 or negative 212, is less exothermic? Positive 6. Less exothermic, prop 2 is the rate determining step. So when we come back, we might get this problem done before Monday. That's great. When we come back, we're going to discuss things like transition states. I don't think we've ever discussed those before. And then we're going to talk about termination steps, which won't take long at all. So we're going to talk about rate determining steps being early or late in their transition states and what those look like. Look forward to that. See you very soon.